So if you don't have LDA, how else could you accomplish this type of reaction, this alkylation transformation at the alpha carbon? Well, one of the oldest methods is with the aldol condensation. So the aldol condensation and reduction. Okay, how does this work? Now, if you've been following along, the aldol condensation does not make an alkylated product. It makes an alpha-beta-unsaturated ketone. But we can take that alpha-beta-unsaturated ketone and reduce the alkene to make the alkene go away. So, what if we took this ketone, and you know, this is my favorite ketone, it's quick to draw, and we treat it with an aldehyde and a nice base. Now, remember, we can't use sodium, we can't use LDA. We have to use a weaker base. Now, this base, sodium methoxide, will certainly not form a super high concentration of the enolate. In fact, it's less than 1% of the enolate. However, when that enolate forms, it reacts and attacks the aldehyde carbonyl. Now, so let me make this a little more complete. This is reversible. So we'll hit about, let's say, 0.1% as our concentration of this enolate. But as soon as this enolate reacts, its concentration is dipped. The equilibrium of this first reaction, or deprotonation, has been perturbed. And what happens? More of our starting ketone will therefore get deprotonated to restore the concentration of our enolate. So even though we don't get much enolate, as that enolate gets siphoned off and reacts with our aldehyde in the next step, then we see we'll form more and more enolate. So we slowly get our enolate to form. So we don't have a super strong base, but over time we're able to get this reaction to continue and proceed. Now, once we get to here, we get our tetrahedral intermediate. There's no reason to show this whole mechanism, but eventually, after multiple more steps, we'll form a beta-hydroxycarbonyl, and that will end up losing water, and we get to here. Now, here's our alpha-beta-unsaturated ketone. That is not our desired product, which we show here at the top of the screen. So to get this, we need to do a second step, and that's going to be simply do a hydrogen over palladium hydrogenation, a reduction of that alkene. And in net, after two steps, one, treating our ketone with an aldehyde base, and then doing hydrogen and palladium, we can make an alkylated ketone. So this is really handy, but there are a lot of limitations to this. Let's just think about those quickly. One, your aldehyde can't have alpha hydrogens. Whoops. So our aldehyde can't look like this because our base would say, oh, those are some nice, tasty alpha hydrogens. And it would know to deprotonate the ketones alpha hydrogens. It might go after the aldehydes alpha hydrogens. So we're really limited on what aldehydes we can use. And what that means is we're really limited what R groups we can put on this product in the bottom right. That's probably one of the main limitations you find in this reaction. We can't make all the things we want. So we say we have limited scope in this reaction. Regardless, for some products, it's a really effective reaction. So early in chemistry, this is one of the best ways that chemists had to make alkylated ketones.